Welcome to 6.6. These are officially our properties of definite integral properties. We've talked about these kind of here and there, but we're going to actually define them for you so that you can use them from here on. The biggest thing that you could remember in this whole unit is that the integral stands for, so in this case, the specific integral from b to a of f of x dx is the accumulating area from a to b under the graph of f. So just like a little sketch over here on the side. If this is f of x, and this is a, and this is b, then what the integral stands for is the area here. So that's just like very basic. That's what we've been talking about for a couple of weeks now. But now we're going to talk about just like some rules that come from this. And so there's some descriptions here and some examples, but a lot of them are like, they just make sense. They're pretty logical. You could have used your own intuition to figure this out. So for example, the zero property rule. Let's say that our bounds on our integral are the same, a and a, right? If our bounds are the same, that means that the area under the curve is going to equal 0. And that honestly just makes sense. So again, let me give you a little sketch here. We'll use some different colors. So this is going to be f of x, and then here's a. And essentially what this is saying is it says find the area from a to a, but that's just like, I mean, that's just a straight line. There's no area there, that's just a length. And so the area under the curve is 0 because there's no area here. And so if you ever see it, it could be a to a, it could be 3 to 3, 0 to 0. That answer is automatically 0 because there's no area there, there's just length. Area has to be like a box or something. So that's the first one. The next rule is additivity, and that essentially says that the integral of f of x from a to b plus the integral of f of x from b to c equals the integral of f of x from a to c. And again, this one just like, it makes sense. I'm going to draw a picture of it. So here is our little curve, and let's say that we are asked, so we have an a, a b, we have a c. So what this is saying is that the area under the curve from a to b, so this space right here, and then it's saying plus the area under the curve from b to c, that just equals the area under the curve from a to c, right? That's pretty obvious. Like you just would add those together. And so this area plus this area equals this whole area. That's how like a triangle would work, right? Or a square. Like if I had a square here and I was like, find the area, I could either, if this was like 3, 4, and 7, I could either do 4 times 7, which is 28, and 3 times 7, which is 21, and add those two together, or I could add these together, 7, and then do 7 times 7, that's 49. You get the same answer either way. Same idea. This next one we've talked about before. It's called the order of integration. And so the big idea here is that the bounds have to be low to high. And in representations we use with integrals, A represents our low, B represents our high. And so if you look here, this is backwards than it normally is. My larger bound is below and my upper bound is above. And so to fix that problem, to actually evaluate, you'll flip the integral. So see, these are flipped, and then you'll add a negative sign. And this one is like a little harder to explain, but I will try my best here. So I'm going to write like a little description, A to B. And so essentially reversing the limits of integrals changes the sign of definite integrals. So that's what that means, right? So if you want some of these like phrases, I'm going to write this, reversing the limits. This is just translation of that notation. Reversing limits of integration changes signs. And so essentially you need to go left to right. So if you go left to right, your area is going to be positive. But if you view this right to left, your area is going to be negative. And one concept that like sometimes helps me think about it is like velocity, right? Like velocity, you always think left to right. It would change it if you were to view a situation backwards. There is more of an explanation too if you guys want to look at a proof of this. One thing it has to do with is when we were using this notation, right? We were doing like earlier when we were trying to find the width of our Riemann sums, when we were doing the width of those rectangles, we were doing b minus a divided by whatever n was, like how many rectangles there are. And if you do it the opposite way, you're going to get a negative out, and you have to be able to deal with that if you do the smaller number before the bigger number. So there's just like lots of reasons why. If you want more of a proof, you can probably look one up on Khan Academy or something like that. Okay, here's the next one. This is called the constant multiple rule. And so these next two kind of go together, but essentially it says if you have an integral, right, and you have a constant within your, like under the integral, you can always pull the constant out. So if you guys see, this was just pulled out, and then you can take the area under the curve, and then you can multiply by that constant. So this was just like pulled out. And so I will show you an example. So let's say that we are finding the integral from 0 to 1 of x dx. So I'm just going to give you a little sketch over here. So this is just like y equals mx plus b. So this is just like essentially y equals x. And so 0 would be right here, right? If I plug in 1 to that equation, I would have 1, 1. So it would be like this. So this is a little sketch of that. And if I were to find the integral, I'd be finding this area right here, which would be 1 by 1 divided by 2, because that's the formula for triangle. So it'd be 1/2, okay? Now let's go ahead and say that I made this 3x dx. So if I were to go and graph this sketch, it would still start at 0, 0, because if you plug in 0 into this equation, you're going to get a 3 out. But if you plug in 0 into this, you're going to get a 0 out. But if I were to plug in, say, a 1, if I plug in 1 here, 3 times 1 is 3. So I'll get 3. So it'll start here instead. And so then this area is now 1 by 3 divided by 2, and that's 3/2. And 3/2 is just 3 times the amount of 1/2, right? If I were to have just done 1/2 times 3, I would get 3/2. And so you're basically just like almost doing a stretch of the area when you do that. But it's just there's no like, it's just a constant, right? It's just a coefficient. So there's no like variable to that. So it doesn't impact anything else. So that's why. Okay. This next one is like kind of a subset of that. So this is just like subset of the constant multiple rule. This is the same idea. If there's a negative inside the integral and you don't want to deal with it, that's essentially just a -1, so you can just pull it out front. So that's it. So big idea for these ones is a constant, if you want it in words, a constant factor can be moved across the integral sign. Okay, so this one is basically saying sum and difference. So this works with sum and difference. So say you're trying to find the integral of a of b of f of x gx. That is the same as the area of a to b of f of x plus a to b of g of x. So let me give you, I'll give you another sketch of this one. So let's say that we are finding the area from, let's do 0 to 1 of, let's do, we'll do x squared. That's going to be kind of hard to do. Let's just do like 2x plus 3. Okay, so we'll do 2x plus 3. So basically what this rule is saying is that this is going to be equivalent to, oh, and I need a dx. This rule is saying that this is equivalent to this right here. Okay, so if I'm assuming, like, I'm considering this function f of x, I'm considering this g of x, I can separate those two. And let me show you graphical representation of what this would look like. So if I were to sketch 2x plus 3, I'm going to need a little bit more space for this, but I would start at 3. And to find my slope, I go up 2 over 1. So it's going to look like this. Oops, wait, don't do that yet. It's going to look like this. And so if I'm finding the area from 0 to 1, I'm finding this area right here. And so that is 1 by 5, and then 1 by 5, so it would be 5/2. So that would be the area of that section right there. If I go and find the area of this, it is just 2x, but it starts at the origin this time. So this is kind of like the one I did earlier. So it starts at the origin, so it goes here. This is at 2. And then I'm finding the area from 0 to 1, so that's 2 by 1. Divided by 2, that's just 1. So I'll write it in different color. So the area of this is 1, the area of this is 5/2. And then finally, this one kind of is a hard one to graph. You might not remember this, but this is just like y = 3, and that's a horizontal line at 3. So if I'm finding this area right here, this equals 3. Oh no, something broke. We'll have to figure out what I did wrong in a second. So then this is 3, so this equals 4. So I obviously did something wrong here. So what did I do? Oh, the very first one I did not do correctly at all. So we need to fix this one. Okay, backtrack here. Hopefully you caught it. I would be very excited if you guys got it. So you should have started at 3 and then go up 2/1. So this actually makes a trapezoid. That's why this one didn't work. Sorry guys, I was like, oh no. Okay, so this is what this one looks like. So this actually makes a trapezoid. I just didn't graph it correctly. So this trapezoid is 3 plus 5 divided by 2 times the base, which is 1. So this is 4. And then, so this is 4. So good. Okay, sorry. So this equals 4. And right, do you see how 1 plus 3 also equals 4? So that's just like me separating them. You'll get the same answer. Sorry if I misled you here. Also, if it was subtraction, it would work the same way. So that's why. Okay. Next one, these ones aren't as popular as some of the older ones, the other ones are, but it's just like, again, just some logic that you could use here. So this basically says if f of x is greater than g of x, okay, on AB, then what it's saying is that the area under the curve of f of x is going to be greater than the area of the curve of g of x. So area under curve of f of x, as long as the bounds are the same, is going to be greater than the area under the curve of g of x. Under the curve of g of x. And again, this is just like, once I draw my sketch, I'll be like, oh yeah, that makes sense. So here is this. My bounds are going to be a, b. I'm going to do my f of x. I'll label it. So f of x, right? F of x is greater than g of x. G of x. And so it's saying that the area under f of x is greater than the area of g of x, which, like, let's just think about this. Like, let's do this sketch. Obviously, this area right here is smaller than this area. So it's higher than the other one, so it's going to work. So that's an example of that one. And then we just have one more, and then we'll do some example problems. This next one's like kind of similar. It's saying that if f of x is greater than or equal to 0, so that means it's all of its y values are always greater than 0, then its integral, its area is going to be 0. So that just means like if it's always greater, right, this area is always going to be positive area. If it was, this doesn't work if it's negative, right? Because if it goes down negative at some point, like even if it was like started here, right, we can't guarantee, and say we wanted the area from here to here, we can't necessarily guarantee that that area is going to be positive. And so that one's just like kind of a logical one. Okay, we're going to do some practice real quick, and we'll start. So for each of the following integrals, if possible. So sometimes you won't even be given a sketch. You'll just be given random pieces of information. Just so you know, sometimes you don't have enough information to answer some of these, and that's totally okay. So this first one says find each of the following integrals if possible. So also up here, I know that the area from -1 under f of x is 5, the area from 1 to 4 under f of x is -2, and then the area from -1 of h of x is 7. So if you guys look at this one right away, the first thing I catches my eyes is that the lower bound is on the bottom. Or sorry, the higher bound is on the bottom. So I need to flip those. So the very first thing I'm going to do is make this -1/4 f of x dx. And then I'm already told that 1 to 4 is -2, so it'll just be -2, and that equals 2. So that's the answer to the first one. Okay, next one, -1 to 4. I'm not given that piece of information, but I do know that -1 to 1 is 5, and -1 to 4 is -2. So I put those two things together, I'll have my answer. So I'm just going to split this between the things that I know. So I know what's going on the curve from -1 to 1. I know what's going on from the curve from 1 to 4. From -1 to 1, it was 5. From 1 to 4, it was -2. So this answer is 3. This next one has like multiple things to it. It has the addition property that we were talking about, and it also has this like these coefficients out front. So I'm going to separate this two ways. First, I'm going to separate, and I'm just going to focus on the f of x part. I'm going to pull the 2 out in front of the f of x and then write f of x dx. So I both separated it from h of x, but I also pulled that constant out. And the next one I'll do the same. I'm separating it, I'm pulling the constant out, and then I'm going to the pieces of information I'm given. So from -1 to 1, it was 5, so I'll do 2 times 5 plus, from -1 to 1 of h, it was 7, so I'll do 3 times 7. So I'll get 10 plus 21, and that's 31. This last one, it asked me from 0 to 1. So here's the thing. I don't know anything about 0 to 1, right? Like, this isn't going to help me. I don't necessarily know what this shape looks like, so I can't just, like, split the answer in half. This is 1 to 4, and this is about h, not f. So sometimes you're going to get these problems, and you need to write, I don't have enough information. Don't do problems that you don't know how to do. Sometimes you need to recognize that you can't do problems with what you've been given. So that is all for that. Hope you enjoyed. Have a good day.